Imagine being told that the thing you've learned about since middle school, the invisible force field surrounding every magnet and every charged particle, the electromagnetic field itself, might not actually exist. Not as a fringe theory, not as some crackpot idea. This is what Richard Feynman, one of the greatest physicists who ever lived, a Nobel Prize winner, argued as a young graduate student at Princeton. And his reasoning is strange and beautiful insight about what fields actually are, would eventually revolutionize our entire understanding of quantum mechanics. He called fields bookkeeping variables, accounting tricks, useful fictions we invented because the true picture of reality was too complicated for us to handle directly. Stop, body. Think about that for a moment. The electromagnetic field, the thing that lets your phone receive signals, that carries light from the sun to your eyes, that holds atoms together. Feynman said, it might just be a convenient mathematical shorthand, a way of keeping track of something deeper and more fundamental. And here's the strange part. He was both wrong and profoundly right in ways that would reshape physics forever. To understand why Feynman made this audacious claim, we need to go back to a problem that had been haunting physicists for decades. A problem so embarrassing, so mathematically ugly, that most physicists simply tried to ignore it. The problem of infinity. You see, classical electromagnetism, the theory developed by Maxwell in the 19th century, has a dirty secret. If you calculate the energy stored in the electric field of a point-like electron, you get infinity. Not a big number. Infinity. The electron, according to the equations, should have infinite mass, infinite energy, and the universe should have exploded the moment the first electron came into existence. Obviously, this did not happen. You exist. The universe exists. Electrons seem perfectly well behaved. So physicists did what physicists sometimes do when faced with an embarrassing mathematical result. They swept it under the rug. They developed clever techniques to subtract infinity from infinity and get sensible answers. They called this renormalization, which is a fancy way of saying we are going to pretend this problem does not exist. But Feynman, as a young student at MIT and later at Princeton, was bothered by this, deeply bothered. He had that rare quality that distinguishes truly great scientists from merely good ones. He refused to accept that nature could be so ugly at its foundation. He refused to believe that the correct description of reality should require infinity-canceling tricks. There had to be a better way. And in searching for that better way, Feynman stumbled upon an insight so radical, so counterintuitive, that it would take him years to work out the full implication. Let us start where Feynman started, with a simple question that turns out to be anything but simple. Why does an electron have self-energy at all? In the standard picture, an electron creates an electromagnetic field around itself. This field permeates all of space, and the field contains energy. The closer you get to the electron, the stronger the field, and the more energy is packed into each tiny volume of space. Now, here is the problem. If the electron is truly a point with no size at all, then as you approach the electron, you keep getting closer and closer forever. The field keeps getting stronger and stronger. And the energy keeps growing without limit. Infinity. But wait, Feynman thought. Why should the electron feel its own field at all? Think about it this way. Imagine you are at a party, and you shout something across the room. Your friend hears your shout a moment later. Sound waves travel from you to your friend, carrying information about what you said. But, do you hear your own shout through the air? Well, yes, in a trivial sense. But that is not really how you hear yourself. You hear yourself directly, through bone conduction in your skull. The sound waves traveling through the air are not necessary for you to know what you said. Feynman asked a similar question about electrons. When one electron shakes, it sends out electromagnetic waves that eventually cause another electron somewhere else to shake. That is how electromagnetic interaction works. Shake one charge, another charge responds later. But does the electron really need to interact with its own field? Is that necessary? What if, Feynman proposed, electrons can only act on other electrons? What if there is no self-interaction at all? If that were true, then there would be no self-energy problem. No infinity. Because the problematic energy came from the electron interacting with its own field, with the field it itself created. Remove the self-interaction, and you remove the infinity. But here is where things get really interesting. If electrons only act on other electrons directly with no intermediary, then what is the field? The answer that Feynman arrived at, working with his thesis advisor John Wheeler at Princeton, was startling. There is no field at all. Or more precisely, if you insist on thinking in terms of fields, then the field is always completely determined by the particles that produce it. The field has no independent existence. It has no freedom of its own. It is just a mathematical convenience, a way of keeping track of which particles shook, and when and how much. You shake this particle and that particle shakes later. That is all that is really happening. The field is just our way of describing this direct particle-to-particle interaction without having to keep track of every single pair of particles individually. Now, you might be thinking, wait a minute, this sounds crazy. We can measure electromagnetic fields. We have instruments that detect them. They must be real. And this is where Feynman made a crucial distinction that most people miss. He was not saying that fields are useless. He was not saying that the concept of a field gives wrong answers. He was saying something more subtle and more profound. He was saying that fields are a description of reality, not reality itself. Think about it like this. Imagine you are managing a large bank. Every day, millions of transactions happen. Money flows from account to account. You could, in principle, track every single transaction individually. Alice paid Bob $5. Bob paid Carol $3. Carol paid Dave $7. And so on, for millions of transactions. But that would be impossibly complicated. So instead, you use account balances. At the end of each day, Alice has a certain balance. Bob has a certain balance, and so on. The balance is a bookkeeping variable. It summarizes the net effect of all the individual transactions without you needing to remember every single one. Is the account balance real? In one sense, yes. You can go to the bank and withdraw money based on your balance. It has real effects. But, in another sense, the balance is just a convenient fiction. The real thing is the individual transactions. The balance is just our way of keeping track of them. Feynman proposed that fields are the same. The real thing is the direct interaction between particles. The field is just our way of summarizing those interactions without needing to track every particle pair individually. But here's where it gets even more interesting. Feynman and Wheeler did not just wave their hands and say fields are bookkeeping variables. They worked out the mathematics in detail, and what they found was remarkable. To make a theory work, to eliminate the self-energy infinities while still getting all the correct experimental predictions, they had to make a strange assumption. The interactions between particles had to involve both advanced and retarded effects. Let me explain what this means. In the normal picture, when you shake an electron, it sends out electromagnetic waves that travel outward at the speed of light. These waves reach other electrons sometime in the future. Cause precedes effect. This is called a retarded wave because the effect is retarded, meaning delayed, relative to the cause. But Maxwell's equations, the fundamental equations of electromagnetism, actually have two kinds of solutions. Retarded waves that travel forward in time, and advanced waves that travel backward in time. Effects that precede their causes. Physicists had always thrown away the advanced solutions as unphysical. Obviously, we do not see effects before their causes in everyday life. But Wheeler and Feynman showed that if you include both types of solutions, in a very specific combination, something magical happens. The advanced waves from the absorbing particles in the future combine with the retarded waves from the source particle in the past to produce exactly the radiation we observe. The advanced effects from the future and the retarded effects from the past conspire together to create the illusion of purely retarded radiation traveling forward in time. Stop and appreciate how strange this is. According to Wheeler and Feynman, when you turn on a flashlight, the light does not simply travel forward in time from the flashlight to your eye. Instead, the flashlight sends out both forward in time and backward in time waves. Wait, the absorbers of light, including your eye and the walls and everything else, send back advanced waves traveling backward in time. And all these waves add up in just the right way to produce what we interpret as light traveling forward. The universe in this picture is far more interconnected across time than we normally imagine. But here is the crucial point for our story. Wheeler and Feynman showed that you can write down an action principle, a mathematical formula describing the motion of charged particles, that does not involve fields at all. The formula involves only the particles themselves and their direct interactions, with a time delay equal to the distance between them divided by the speed of light. The action is a sum over all pairs of particles. Each pair contributes a term that depends on whether their space-time interval is zero, meaning whether a light ray could connect them. If the interval is zero, they interact. If not, they do not. No fields anywhere, just particles interacting directly along light cones. Feynman wrote this action principle in his thesis. It was mathematically elegant. It eliminated the self-energy infinities. It made perfect physical sense. And then he tried to turn it into quantum mechanics. This is where things got really interesting. The standard way to do quantum mechanics, developed by Heisenberg and Schrödinger and others, requires something called a Hamiltonian. The Hamiltonian tells you how the quantum state changes from one instant to the next. It encodes all the rules of the game. But here is the problem. The Wheeler-Feynman action, with its direct particle interactions involving time delays, could not be written in Hamiltonian form. Think about why. The Hamiltonian method requires you to know everything about the state of the system at one instant of time. Given that snapshot, you can calculate the next instant. But with time-delayed interactions, you cannot do this. To know what happens to a particle now, you need to know what other particles did in the past. The history matters. So Feynman was stuck. He had this beautiful classical theory that eliminated infinities, but he could not quantize it using standard methods. And this is where his genius really shone. If the standard methods will not work, he thought, then I need to invent new methods. He went back to first principles. What is quantum mechanics really about? What is the essential core idea? And he found his answer in an old paper by Dirac. Dirac had shown that there is a connection between the exponential of the classical action and quantum mechanical amplitudes. It was a mathematical curiosity, not fully developed, but it pointed in a direction. Feynman ran with it. He developed what we now call the path integral formulation of quantum mechanics. Instead of thinking about wave functions evolving in time, you think about particles taking all possible paths through space-time simultaneously. Each path contributes an amplitude, a complex number, that is the exponential of I times the action for that path, divided by Planck's constant. The total amplitude for a particle to go from point A to point B is the sum of the amplitudes for all possible paths. This sum over paths is what we mean by the path integral. And here is the beautiful thing. The path integral formulation does not require a Hamiltonian. It works directly with the action. Even for actions that involve time delays. Even for the Wheeler-Feynman action without fields. Feynman had invented an entirely new way of doing quantum mechanics, all because he wanted to get rid of fields. And in this new picture, what are fields? They are bookkeeping variables. Let me explain this more carefully, because it is a subtle and profound point. In the Hamiltonian formulation of quantum mechanics, you need to specify the state of the system at each instant of time. For a theory with time-delayed interactions, this is impossible because the past matters, not just the present instant. But you can fake it. You can introduce extra variables that encode the relevant history. These extra variables keep track of what happened in the past so that you can pretend the system is instantaneous. These extra variables are the fields. The field at a point in space is, in this view, nothing but a record of which particles shook in the past in such a way that their influence is reaching that point now. The field summarizes the history. Traits. The one summarizes the history. It is a memory device. A bookkeeping entry. Feynman put it this way in his Nobel lecture. From the overall space-time view of the least action principle, the field disappears as nothing but bookkeeping variables insisted on by the Hamiltonian method. The fields are not fundamental. The particles and their direct interactions are fundamental. The fields are just what you need to bolt on to make the Hamiltonian method work. But here is the twist. The Hamiltonian method works incredibly well. It gives correct answers. It makes accurate predictions. The bookkeeping variables are extraordinarily useful, and this raises a deep philosophical question. But if a mathematical entity gives correct predictions about the behavior of the universe, in what sense is it not real? This is where we need to step back and appreciate the bigger picture. Feynman started with a simple motivation. He wanted to get rid of infinities in classical electromagnetism. He proposed that electrons only interact with other electrons, not with themselves. This led him to conclude that there is no independent field, only direct particle-to-particle interactions with time delays. Trying to quantize this theory forced him to invent the path integral formulation of quantum mechanics, one of the most powerful tools in all of theoretical physics. The path integral gives an entirely different way of looking at quantum mechanics, one that makes certain things obvious that are obscure in the standard formulation. But here is the irony. The specific theory that Feynman and Wheeler developed, the absorber theory with half-advanced and half-retarded waves, turned out not to be the complete description of nature. When physicists tried to use it to explain certain subtle quantum effects, like vacuum polarization, it gave wrong answers. Feynman eventually had to admit this. In a letter to Wheeler in 1951, he wrote, "I wish to deny the correctness of the assumption that electrons act only on other electrons. The fields, it seems, are more than just bookkeeping. And yet, Feynman's insight about the nature of fields, developed in his youth, continued to shape his thinking for the rest of his career. The path integral formulation that he invented, trying to make his field-free theory work, became a standard tool in quantum mechanics. His way of thinking about particles interacting directly along light cones became the foundation for his famous Feynman diagrams, the pictorial method for calculating quantum processes that revolutionized particle physics. And the question he raised, the question about what is truly fundamental and what is merely a mathematical convenience, remains one of the deepest questions in physics. Let me tell you what physicists today think about this. In modern quantum field theory, the fields are taken as fundamental. The particles emerge from the fields as excitations, like waves on the surface of the ocean. The electron is not a little ball, it is a ripple in the electron field. The photon is not a particle, it is a ripple in the electromagnetic field. This is the opposite of what Feynman originally proposed. Instead of particles being fundamental and fields being bookkeeping, modern theory says fields are fundamental, and particles are, in a sense, the bookkeeping. But here is what makes this so fascinating. Both pictures work. And both give correct answers. Both can be used to calculate the outcomes of experiments. And this hints at something profound about the nature of physics itself. Feynman once said, "The same equations have the same solutions." What he meant was that if two different physical pictures lead to the same mathematical equations, then they make the same predictions. And if they make the same predictions, you cannot use experiments to decide between them. Which picture is correct? Particles acting directly on each other with fields as bookkeeping, or fields rippling through space-time with particles as localized excitations? Maybe that is not even the right question. Maybe the deepest level of reality is not describable in terms of either particles or fields, but in some more abstract mathematical structure that can be interpreted either way depending on what is convenient. The action principle, which Feynman loved, is like this. The action does not care about particles or field. It just specifies the total behavior of the system across all of space-time. You can derive particles from it. You can derive fields from it. But the action itself is something more fundamental than either. And this brings us to perhaps the deepest insight from Feynman's journey. He started wanting to eliminate fields because they led to infinities. He invented revolutionary new mathematics trying to quantize his field-free theory. He eventually had to abandon his original idea because it did not quite work. And yet, nothing was wasted. The path integral formulation he invented became indispensable. His way of thinking about particle interactions became the foundation for Feynman diagrams. His philosophical stance, always questioning whether the standard picture was the only picture, freed him to see possibilities that others missed. Feynman once said something that captures this perfectly. He said perhaps a thing is simple if you can describe it fully in several different ways without immediately knowing that you are describing the same thing. The electromagnetic field and the direct particle interaction picture both describe the same reality. They look completely different, but the mathematics proves they are equivalent. This is one of the great mysteries of physics. Why should nature admit multiple descriptions? Why should there be more than one way to capture the truth? Perhaps because the truth itself is beyond any single description. Perhaps because our human concepts of particles and fields and waves and forces are all approximations to something deeper. Something we can approach from multiple angles, but never quite grasp directly. Feynman never stopped asking these questions. Even after winning the Nobel Prize for his work in quantum electrodynamics, he remained dissatisfied with the foundations. He knew that the renormalization techniques that swept the infinities under the rug were not truly satisfying, even though they worked spectacularly well. He wanted to understand not just how to calculate, but why the calculations work. And that perhaps is the greatest lesson we can take from his story. The bookkeeping variable insight was not just a technical idea about fields and particles. It was an attitude, a willingness to question the most basic assumptions, a refusal to accept that the standard picture must be the correct picture, a faith that nature at its core must be simple and beautiful, even when our descriptions of it are complicated and ugly. That attitude led Feynman to some of his greatest discoveries. And it remains essential for anyone who wants to push the boundaries of our understanding. We still do not have a complete, infinities-free theory of quantum electrodynamics. We still do not know whether fields or particles are truly fundamental, or whether that question even makes sense. We still face deep puzzles about the nature of reality at its smallest scales. But we have Feynman's example, his willingness to ask whether there really is a field, his invention of new mathematics when the old mathematics would not work, his eventual acceptance that his original idea was wrong, combined with his recognition that the journey had been worthwhile. Science is not about being right. It is about understanding better today than you did yesterday. It is about following questions wherever they lead, even when they lead to dead ends, because sometimes those dead ends reveal hidden passages to unexpected treasures. Feynman followed a question about infinities and fields into an entirely new formulation of quantum mechanics. The path integral lives on, even though the original motivation behind it did not quite work out. That is the nature of discovery. That is the beauty of physics. And that is why, when we ask whether fields are real or merely bookkeeping variables, we are not just asking a technical question about mathematics. We are asking what it means to understand the universe. We are probing the limits of human knowledge. We are continuing a journey that Feynman began as a young graduate student, a journey that has no end. The next time you see a magnet, attract a paperclip, or feel the warmth of sunlight on your skin, or watch your phone receive a wireless signal, remember that behind these ordinary phenomena lies a deep mystery. Are there invisible fields filling all of space, carrying forces from place to place? Or are there particles interacting directly across space-time, with the fields just being our bookkeeping notation for interactions we cannot easily track? The answer might be both, or neither, or something we have not yet imagined. Feynman would have loved that uncertainty. He thrived in the space where questions outnumber answers. He found joy not in knowing, but in finding out. And that, in the end, is what he taught us about physics. It is not a collection of facts to memorize. It is a way of looking at the world with wonder and curiosity. It is the recognition that behind every familiar phenomenon lies a mystery waiting to be explored. There is no field, Feynman said, and in saying it, he revealed how much more there is to understand.